Hello everyone, this is Orhan. Welcome to Clustering Methods lecture. In this lecture, I will introduce you a popular unsupervised learning method called clustering, which refers to a broad set of techniques to find subgroups in a dataset. Let's dive in. Okay, let's review the outline of the lecture. I will first introduce you the idea and then review something we covered before, measuring distance between records. And I will show you how to understand visualization with dendrograms. Clustering is popular in many fields and there exists a number of clustering methods. In this lecture, I will focus on perhaps two best-known clustering approaches, hierarchical clustering and k-means clustering. Okay, clustering is widely used across many fields, many sciences. In biology, for example, it is used for classification of species. In finance, this is used for grouping the securities in a portfolio to decrease the risk. And also clustering is used for grouping firms for structural analysis of the economy. An interesting application is the design of a new set of sizes for army uniforms for women in the US Army. It's also used in social sciences for segmentation of voters. So let's review the basics of clustering. Clustering is an unsupervised problem because we are trying to discover structure, in this case distinct clusters, on the basis of a dataset. The goal in supervised problems, on the other hand, is to try to predict some outcome vector such as survival time or response to drug treatment or default. When we cluster the observations of a dataset, we seek to partition them into distinct groups so that the observations within each group are quite similar to each other, while observations in different groups are quite different from each other. Of course, I will mention in a moment what it means for two or more observations to be similar or different. Take a look at this chart, please. We are now clustering different sizes and different types of balls here. This is a more data-based example. So clustering is not the same, but similar to classification. Take a look at this figure, for example. It illustrates the results obtained from performing clusters in two dimensions, x and y, with three distinct non-overlapping clusters. So to the left of figure, you see the data set. To the right of the figure, you see that it is clusters in three groups. And then they are non-overlapping: blue group, red group, and green group. One might ask how many clusters there should be. The answer to this problem is subjective. You can always use as many clusters as you want, as you can see in this example. So the more clusters you use, the more difficult it becomes to explain the situation. Okay, as I said, there are two general types of classifications: hierarchical methods and k-means clustering. K-means clustering is a non-hierarchical method. Hierarchical methods begin with n clusters and sequentially merge similar clusters until single cluster is obtained. Hierarchical clustering has an added advantage over k-means clustering, which I will explain in a moment, in that it results in an attractive tree-based representation of observations called dendrograms. To perform k-means clustering, we use a pre-specified number of clusters. The method assigns each record to exactly one of the k clusters. This method is generally less computationally intensive and are therefore preferred with very large data sets. Now, before we move to the details of these two methods, let's review how we measure the distance between groups. The most popular distance measure is Euclidean distance, which is calculated as follows. We take the square root of the summation of square differences between the dimensions or the features of the data set. So let me illustrate this on an example. In this course, I will analyze stock market data, focusing on a data set comprising of 25 stocks. Each stock is characterized by two features, average return and beta. The first feature is the annual average monthly return observed from December 2013 to December 2023. This metric provides insights into the stock's performance over this period. For example, Apple's average monthly return in the last 10 years is 2.2%, it's per month. Alphabet's is 1.5%, and Amazon is 2.1%. So the second feature is the annual beta, calculated by regressing the stock's return against the returns of S&P 500 index. So details is not important. Right now we have beta, and beta value serves as an indicator of stock's volatility relative to the overall market, offering a measure of systemic risks. So the first column is the return, second column is the risk. Now let's calculate the difference between Apple and Alphabet. What we are going to do is we are going to take a look at two dimensions. So this is the difference between the first dimension, which is average return. So average return of Apple minus average return of Alphabet squared. And the second term belongs to beta, Apple's beta minus Alphabet's beta squared, and then the result of this calculation gives us 1.2. So 1.2 is the distance between Apple and Alphabet. So the problem of this method is that this distance measures are highly influenced by scale of measurements. The solution is to normalize the data first. So we are going to subtract the mean from each observation, each record, and divide by standard deviation, also called z-score. The other solution is rescaling it to 0-1 range. So we are going to kind of normalize everything from 0 to 1. So there will not be anything less than 0, more than 1. So we are going to subtract the minimum, divide by range. This is another method. So let me show you the data set again. So the left panel shows you the original data, and the right panel shows you the normalized data. So I'm going to review what I did up to now in Python. Before starting the coding in Python, let me show you the dataset that we are going to deal with. This is an Excel sheet called stocks. In column A, we have the companies. In column B, we have average monthly returns. In column C, we have beta. Now let's open a Python file and import the dataset. Okay, let's start with the libraries. So these are the libraries that I will be using. Let's run it. And now we are going to import the dataset. Okay, the first line imports the data. Second line sets the first column as an index. So I'm going to use company names as an index. And now we see the first 5 rows of our data set. Now let me draw a scatter plot of the beta and average return. The first 2 rows of this code draws the scatter plot, and the second 2 rows just annotates the data. It shows the names of the companies in the dataset. As you can see, the 2 most distinct companies are Nvidia and Tesla. The others are more or less gathered around here. So what we did a moment ago is to calculate the distance between Alphabet and Apple, which is here. We just measure the distance between Alphabet and Apple as 1.2. So this distance is measured as 1.2. Now let me show you how to find the pairwise distances between the companies. Okay, so this matrix shows all possible distances between the companies. As you might remember, we found the distance between Apple and Alphabet as 1.2 and 1 a moment ago. Now you can see all possible combinations here. But these distances are not normalized. So let's calculate the normalized differences between the companies as follows. Now these are the normalized distances. Okay, so this was the method to calculate the difference between the records or the observations. How about the clouds? How can we calculate the distances between the clouds? Well, there are a couple of methods. Let me illustrate them on this figure and explain this. The first method is called single linkage. Single linkage is the distance between the pair of records, for example, A and B, that are the closest. So this is the minimum distance, and this is called single linkage. The other method is called maximum distance or complete linkage. That is the distance between a pair of records A and B that are farthest from each other. So in Portugal cloud, this is the farthest. In France cloud, this is the farthest. So that's why that's the maximum distance. The other one is called average distance or average linkage. It is the average of all possible pairwise distances. And centroid distance is the distance between two cluster centroids. So this is the centroid of France. This is the centroid of Portugal. So that's why this distance is called centroid distance. So this is basically just visual explanation. So now we can take a look at the first one of the clustering methods, which is called hierarchical clustering. In hierarchical clustering, there are three main steps. First, we start with n clusters, so each record is its own cluster. And then we merge two closest records in one cluster. And at each successive step, the two clusters that are closest to each other are merged, and at the end, we end up with only one cluster. So dendrograms illustrates this. Let's take a look at one dendrogram, which probably explains the situation better. Okay, so this is the figure that I illustrated a moment ago. It's basically a scatter plot in 2 dimensions. In the right-hand panel of figure, each leaf of dendrogram, so these are basically the leaves, represents one of the 25 observations. However, as we move up the tree, some leaves begin to fuse into branches. And these correspond to observations that are similar to each other. As we move higher up the tree, branches themselves fuse either with leaves or other branches. The earlier or lower in the tree fusion occurs, the more similar groups of observations are to each other. On the other hand, observations that fuse later near the top of the tree can be quite different. In fact, this statement can be made precise. For any two observations, we can look for the point in the tree where the branches containing those two observations are first used. The height of this fusion, as measured on the vertical axis, indicates how different two observations are. Thus, observations that fuse at the very bottom of the tree are quite similar to each other, whereas observations that fuse close to the top of the tree will tend to be quite different. Now let's draw this dendrogram in Python. So these are the clustering of my companies. As you might remember, Tesla and Nvidia were the farthest in the data set. So that's why they fuse the latest. So they don't fuse at all in the initial stages. First of all, Apple and Adobe, which are the closest ones here, they merge first. And then like other companies start merging here at the earlier step. Tesla and Nvidia, they never merged until some point here. And then at the end, these two, Tesla and Nvidia, and all others merge in the last step. So as I said before, observations that fuse later can be quite different, Nvidia and Tesla. And for any two observations, we can look for the point in the tree where the branches containing those two observations are first fused. So these are the companies which are first fused. So these are the closest companies. We can draw the same dendrogram with another method. So in this method, we use the single linkage method, which is the minimum point in the clusters. We can use the same thing with average. I just copied and pasted here. The only difference here is going to be the average. So I just changed this to average. We again more or less have the same situation. Tesla and Nvidia merges the last, and the others are merging earlier. This was a visual representation. Now I can list the clusters. So this code basically cuts the hierarchical tree from the point we specify here. For example, I'm saying that cut it when there are 4 clusters, which is exactly somewhere around here. So if I say 4, it cuts somewhere around here, like somewhere around 1.5 here. So 1 cluster here, Tesla, NVIDIA, 1 here, 1 here, and 1 here. So if you say, for example, 2, you would see that there is only NVIDIA, Tesla on one side and everything else on the other side. So which is exactly the dashed line here. So Tesla, NVIDIA. So look at the like dashed line I'm cutting here. I am literally telling the code to cut when there are 2 clusters. So 1 cluster here, 1 cluster there. So this cluster to the right basically encompasses all of the companies. Or you can make it 6. So 6 clusters is okay. This is a cutting mechanism in hierarchical clustering. Now let me show you a heat map of these clusters. This is the heat map for 25 companies. Rows are sorted by 6 clusters, as I just showed here. So rows are sorted by 6 clusters from single linkage clustering. Darker cells denote higher values within a column. This is all about hierarchical clustering. Now let's take a look at k-means clustering. So these are the 6 clusters using k-means clustering. As you can see, Tesla and NVIDIA is still a separate group because they are furthest. But in k-means clustering, the only difference in k-means clustering is you are supposed to write down, give in advance how many clusters you want to. I just asked for 6 clusters. That's why it just gave me 6 clusters. If I change it to 4 and then rerun the code, there are 4 clusters now. Tesla and NVIDIA is still separate. So lastly, I will show you the relationship between number of clusters and average within cluster square distances. So this is showing us the relationship between the average within cluster square differences and number of clusters. As number of clusters increases, average within cluster square distances decreases. But as you can see, after some point, it's okay. So from 1 to 2, the square differences decrease substantially. From 2 to 3, again, very big difference. But from 3 on, the decrease in average within cluster square differences is not that substantial. So for example, choosing between 5 and 6 clusters does not matter a lot. Well, that's all about cluster analysis. If you want to learn more about the methodology and the theory, you can take a look at Chapter 12 of An Introduction to Statistical Learning or Chapter 15 of Data Mining for Business Analytics. They are going to give you more in-depth information. I hope you enjoyed this video and hope to see you in the next videos. Bye.